And team three, if you want to go ahead, you can start sharing your slides. I'll do a quick, I guess, reintroduction. So again, welcome to the WMU Civil and Construction Engineering Senior Design Conference as we roll on with some more presentations this morning. And here we'll start with our third presentation of the day. I'd like to welcome our industry advisory board members. I think I got most of them. I don't know if I missed anybody. I apologize. Lots of students out there too. It's a great way to do this, get a lot of participation. So thank you for being here. It's an exciting day for our graduating seniors as they present the fruits of their labor over the last academic year. So some great work by our students. Get to share that today on their big day. They look toward graduation here in about a week and a half. So congratulations to our seniors. And with that, team three, the structural design of a new concessions building for the Forest Hills Public Schools. Gentlemen.
Hello and welcome to our senior design presentation. We will be talking about the structural design of a new concessions building for Forest Hills Public Schools. Our team consists of Joe Belka, Cesar Hernandez, Jean-Luc Lachance, and Jarrett Nyan. This was done in conjunction with Tower Pinkster, our sponsor, and through the Civil and Construction Engineering Department at Western Michigan University. Today, we will be introducing our project, talking about the scope, the structural analysis, masonry design, floor design alternatives, foundation and retaining wall design, our steel design, our detailed cost estimate summary, our sustainability, construction plan sheets, summary, and acknowledgements. So why a new building? Bonds have been passed to increase the infrastructure of the athletic facilities at Forest Hills Public Schools. The old concessions building had limited storage, limited locker room space, and limited kitchen space for the concessions. Due to the bonds being passed, we are able to demolish this existing structure and design the new structure to have more locker room space, more space for storage, and a larger area for the kitchen.
Before I introduce our scope, I want to talk about the three design stages that are typically done in a construction project. First is the schematic design. Not a lot of structural engineering is done in this design, as it's mostly the architects and planners determining the size and layout of the building. Next is the design development stage, which is where a lot of the structural engineering is done, mostly selecting member sizes, determining wall construction and reinforcement, as well as footing reinforcement, and also roof design. Finally, the last stage is the construction document stage. That's where a lot of the specific detailing is done, including the connection design. And what we're specifically including in our project is the structural and geotechnical design of the foundations and retaining walls, the CMU masonry walls, the steel lintels, and any other miscellaneous steel framing. We're also going to be doing a material cost estimate, and we have produced some construction plan sheets at design development. Specifically not included in our project is the roof construction. The wood trusses and sheathing are going to be designed by the supplier, as well as precast concrete will also be designed by the supplier. Specifically in our cost estimate, we are only considering material and excluding labor and equipment costs. Finally, as I stated before, connection design is not in this stage of design. The first step of any structural design project is to determine the loads that are going to be acting on the building. We considered 5 different loads on this building, being the dead loads, live loads, snow, wind, and seismic loads as well. For the snow, wind, and seismic loads, we gathered some preliminary data from ATC Hazards by Location website for the location at the site that we chose. We also used ASE 710 to develop the dead, live, snow, and wind, and seismic loads. And then finally, Tekla Tedds was used to check our hand calculations and confirm those calculations as well. As you can see on the bottom, we used ASE 710 LRFD load combinations in this project. And on the right side of the screen, you can see that there is an example of our dead and live loads that were used in designing this project. Here is a section view of what our building looks like. And on the right side, you can see that we have a beam supporting the canopy, as well as a column that's attached to the beam to carry the load down into the soil. And there's also going to be a strip footing along the exterior of the building, as well as a basement retaining wall in the middle of the building to hold back soil and also support the floor construction above the basement. There's also a concessions and restrooms on the front side of the building, and the locker rooms are on the back side on the first floor and in the basement, as well as some storage that can't be seen here.
For our masonry design, a few considerations were made. The first was that the components and cladding method for windmills controlled our design. This was used opposed to LRFD because it gave higher design pressures and we wanted to design for the highest values. Our design assumptions for reinforced masonry were made according to TMS 9.3.2. We assumed our bars to be spaced at 16 inches to account for any error and to have a more conservative design. The CMU wall was treated as a beam with uniformly distributed load for our wind calculations. The masonry alone was adequate to support the axial roof loads and no additional reinforcement was necessary for this. The first table here shows our design results. For the first floor wall, for both zones 4 and 5, we selected a number 7 rebar to be spaced at 16 inches. The basement wall, for zone 4, we selected a number 5 bar, and for zone 5, we selected a number 4 bar. The second table here gives our final design. For consistency and a more conservative design, we selected a number 6 bar spaced at 16 inches on center under the first floor, and a number 7 bar spaced at 16 inches on center above the first floor.
For our floor construction above the basement wall, we considered two alternatives, one of them being a precast concrete plank and the other being a cast-in-place concrete slab on metal deck supported by steel joists. The precast concrete plank was selected to be a 10-inch hollow core plank with a 2-inch topping. This is going to be designed by the supplier and it's also much simpler in construction as seen in the picture. For the cast-in-place slab on deck with steel joists, we selected 24-inch LH06 steel joists as 5 foot on center per the Steel Joist Institute, and also 4 3/4-inch composite slab with a metal deck. And also the minimum reinforcing will be provided to prevent temperature cracking in the concrete. To compare these two floor systems, we used this table and 5 different performance categories to select which floor system to use. All the categories were weighted equally, and the scoring was 1 through 5, with 5 being the high score. So between the 5 categories, the cost, constructability, and compatibility with other trades are really where the floor systems differed, with the precast plank being better in all 3 of those categories. For sustainability and structural performance, they were pretty equal, and finally, we selected the precast concrete plank as our floor system.
For our foundation design, there were several considerations that had to be made before selecting the size and the rebar layout for the footings. First was the maximum bearing pressure of 3,000 pounds per square foot. The top of the footings will be 42 inches below grade to counteract the frost action. They'll be placed on a backfill meeting MDOT Class 2 requirements. LRFD loading will control, and the water table is at 7 to 13 feet. Much of this information was given to us by our sponsor through a geotechnical report, and there were several variations of footings used in our design. First, underneath the canopy columns, we selected a 4x4 square footing. Under the exterior masonry walls, we used 3.5 foot wide strip footings, and we placed a retaining wall on the southeast side of the basement wall. As you notice, this is an academic version of Risa foundations. This is to show our rebar detail for our square footing underneath the canopy. You can see that we have 6 number 4 rebars going both ways for the footing, as well as a 2 foot by 2 foot pedestal that will have 8 number 6 rebars supporting. Here is the strip footing details for our reinforcement. You can see we chose 2 number 6 bars at 18 inches on center at the top and the bottom of the footing, as well as 6 number 4 bars at 18 inches on center for temperature and flexural reinforcement. Here is a schematic for our retaining wall details for our reinforcement. You can see we chose 2 number 6 rebars at 18 inches on center, as well as number 4 rebars at 18 inches on center. We chose a stem width of 1 foot, as well as a toe length of 3 feet and a heel of 5 feet. Much of these calculations were done with ACI specifications and using Risa foundation.
For steel design, a few considerations were made. The first was that the loads from the roof transfer diagram were used for our design calculations. AISC tables 1-1, 3-2, 3-10, 4-4, and specification section GA8 were used for our design. Columns, beams, bearing plates, and lintels were in the scope of our steel design. Connection design was not in this phase of the project and was outside of our scope. We used a factor of safety to account for any error and to have a more conservative design. For our bearing plate, we assumed square plates. The first member design was the beam supporting the canopy. We had to ensure that our available strengths were higher than the required strength. Keeping this in mind, we were able to select a W8x21 for the beam supporting the canopy, and tables 3-10 and 3-2 to the right show our design values and the tables we got them from the steel manual. For our canopy column, we needed to interpolate between 12 and 13 feet of effective length to design for 12.5 feet of effective length. Using tables 4-4 to the right, we were able to obtain a design strength of 60.2 kips, which was higher than our required strength. We selected an HSS 4x4 by 3/16 for our canopy column. For our bearing plate, we selected a 6x6 by 5/8 inch plate, which had an available width and available thickness higher than the required width and required thickness.
It's the structural and geotechnical design. A detailed cost estimate was performed, showing all the material costs for the permanent elements of the building. For the material takeoff, the team used Bluebeam Revit. And for material pricing, we use RS Moons. In this estimate, the team specifically only considered the material to construct the building. Therefore, many trades were excluded. Trades such as project management, supervision, daily labor, and equipment were excluded, along with the excavation and demolition of the building. Here we can find a detailed breakdown of material cost. The figure illustrates a summary of the cost for each trade, the cost per square foot, and the total cost before overhead, profit, insurance. Total was around $733,000, and after overhead and profit, it came to a value of $953,000. We found that the unit cost of concrete reinforced wall was the line item with the highest cost due to the thickness of the concrete. The division which represent the highest material cost were masonry, concrete, and finishes. This is shown in the pie chart representing the total distribution of material cost. The gross square foot of the building is about 6,000 square feet, and the total cost was approximately $122 per square foot. Besides the masonry, trades such as doors and windows represented a valuable amount of money in the cost estimate. Divisions for the highest amount of money were Division 4 and Division 9. Division 4 was masonry, and Division 9 was finishes.
As with any civil engineering project, sustainability is incredibly important to provide a clean environment for future generations. According to AISC, the American Institute of Steel Construction, 93% of American structural steel is made from recycled material, and 98% of structural steel can be recycled at the end of the structure's life cycle. This should be taken into consideration when demolishing the existing structure at Forest Hills Public Schools. Masonry and concrete sustainability. This considers a high thermal mass, which can lead to reduced energy costs, a smaller HVAC systems, and masonry and concrete is also highly recyclable and can be crushed and used as aggregate in future projects. When demolishing the existing structure, demolished masonry and concrete will be recycled. For any design considerations using recycled materials, it is suggested that you go to the engineer for approval.
In final summary of our structure, we are going to talk about our Risa 3D model. Here's an overview of the 4 different directions, and we will be going into detail for each of those. Here is a direction from the south, and as you can see, we have our beam right here supporting the canopy, and also a column that goes into a bearing plate onto a concrete pier. The footings can't be seen in this view because Risa 3D does not support drawing footings in this because they have a separate program called Risa Foundations for that. We also have many openings in our masonry walls, and quick note is that our wooden trusses that are depicted here are not actually being used in the design. These are just modeled for aesthetic purposes only. Here is a backside view of the building. As you can see, the foundation walls do step up as they go up the grade. This is to save money and also keep the walls under the frost action level. Here's another view. And for all of these openings in the walls, we had to design lintels for the construction. And a lot of the windows and doors were the same size, so a lot of the lintels could be reused. Now we'll talk about an overview of our foundation plans. This is the overall foundation plan that we drew up. And as you can see, we selected a 4-inch slab on grade at the two different levels here. The basement level is at 90 foot and the first floor level is at 100 foot. So there's a 10-foot difference there. And then also we have dimensions and height callouts that we'll go into detail for. Here is the southwest wall. And as you can see right here is our basement retaining wall. The SF here stands for step footing. So this illustrates that the footing is going up in height. So that's going to be shorter overall because frost action does not need to be designed for in the middle of the building, only on the exterior walls. And some other stuff is called out here too. This is the back wall of the building. As you can see, we have openings here in our wall for the contractor to design and construct. This is the same wall as the southwest side, but it's on the northeast because this building is symmetrical. And then this is our front wall of the building. As you can see, we have our 2-foot concrete piers on top of our 4-foot square footings. Here are our two details, which are the same thing as what Jean-Luc illustrated from Risa Foundations. The only difference is that we designed also for a brick ledge for the exterior footing wall, and that there's going to be a clear spot for the masonry contractor to place the CMU block on top of, and it's also going to provide a backing for the face brick that will be installed by the contractor. Here in the retaining wall footing detail, we can see that the precast plank is going to bear on top of the retaining wall, as well as a thickened slab from the slab on grade for the concessions room will also bear on top of that. So all of the reinforcing is the same as what was illustrated from Risa, and that will bring us into our framing plans. Here is our two framing plans that we have. These are our first floor framing plan on the left and our roof framing plan on the right. Going into detail for the first floor framing plan, we can see here that we call out dimensions and lintel types. L1, typical is for the face brick lintel that is going to support all of the brick on the exterior of the building. And there's also other lintels called out, as well as the masonry wall construction. On the sheets, there is a schedule for masonry wall construction that calls out reinforcing. Here in the precast loading plan, this shows different hatch patterns for the different live loads that are going to be acting on the precast. And that is going to be supplied to the precast supplier. On the left is the storage room, which is 125 pounds per square foot from ASE 710. And on the right is a locker room and hallway, which is for 100 pounds per square foot of live load. Here is our canopy framing plan. As you can see, we call out our beams and our columns with the base plates, as well as the top of steel elevation and also the slope direction of the roof and the roof construction. Next is the rest of the roof framing plan. We call out the 2-foot wood trusses on center, and those are to be designed by others, and also The framing is shown for schematic purposes only. And also we show the built-up trusses on the roof, as well as the sloping direction and any lintels that are below the roof on the first floor. Finally, we would like to say a big thank you to our sponsor, Tower Pinkster, specifically the structural engineers there, Amanda Ruffing and Ryan Ebersole. Without you guys, this project would have never been able to happen, and thank you for the resources. Also, we'd like to thank the Western Michigan University Civil and Construction Engineering Department, specifically our faculty advisors, Dr. Otaniake and Dr. Shao. Thank you for your advice and your help along the way. And also, thank you to our senior design coordinator, Dr. Haynes, for your endless leadership and great thoughts and feedback that you've given us throughout our years at Western. At this time, we'd like to open up the floor for questions. Thank you for listening.
Excellent. And at this time, I do want to welcome, before we get into questions, I do want to welcome 4 of our industry advisory board members. Anna Horner has joined us. Anna, thank you for being here. Chaz Hammond is also here, as well as Janine Cooper and Jason Raleigh. So thank you. More of our industry advisory board members, as our schedule allows, are able to join us. So thank you for being here. And with that, questions? This reminds me of class.
Yeah. Hello, team. Nice job. So I have a question regarding to the foundation design. So you mentioned you use the Risa foundation software for your foundation design. Just want you to give us some little more details, like what's the input you give to the software, what's the output you got, and then how do you verify the design of foundation? What are the checks you made for the foundation design? Yeah.
Yeah, so for our inputs, a lot of it was the geotechnical limits that were given in our geotechnical report. When we got the output, we checked it using ACI specifications. A lot of it was finding the nominal area of steel that was needed for the rebar and the clear spacing cover for that rebar. This was done using ACI 318, the equations there, and Risa was more of a way to get the picture of the reinforcement, and it was checked using equations that we learned in foundation design as well as ACI specification.
So what are the load you considered? And did you check the strength of the foundation you designed?
Yes, the load was 7.8 kips per foot is what we got from the transferring from the roof down to the masonry wall and all the way to the foundation. And based on just my calculations and our calculations through the doing flexural reinforcement design, as well as the size, the bearing pressure, and sizing it at 3.5 feet, we got that it was adequate for the loading that we had on that foundation, our footings.
Okay, sounds good. Thank you. Yes. So following up, I'm curious about the steel frame design, again, similar questions, like where, how did you determine the load on the steel beams you selected? And besides the strength check, I look at like the fracture and shear, did you check the deflection on those beams, under the load?
I guess I can take this. So we did consider deflection with the Risa 3D model. We had specific load combinations that Risa generates, and nothing was above a half inch, and there wasn't really too much load acting on the beams or the columns. Our columns, I would go back, but that'll take time, but we were about 60.2 kips on the column, and our required was much lower than that. So our column had very little deflection, and our beam was also had a pretty good factor of safety. So there was no deflection. Well, there was, but it was very small. And
okay, so yeah, so just make sure you include those deflection check in your report. Like, what's the criteria you check against It's deflection is mainly for beams, not for column. Okay, sounds good. Thank you. Great job.
Other
So,
questions? Oh, go ahead.
follow-up questions to Dr. Shah's one on foundation design. What loads demand the top steel in these foundations? Because I can see top transverse steels are used. The net for the spread footing as well as the strip footing. So what loads demand top steel in these foundations? That's one question. The second one, I don't know if I missed anything, but you were showing that 3D model from Risa and then mentioned the roof is used for aesthetic purpose. So then how did you validate that model with the actual loads that's going to come into these components for component design?
So for the roof, actual design and construction of that wasn't part of our scope. But as far as loads, we assumed some conservative values for that, and then they're going to be pin connected onto the top of the masonry walls. So we then just transferred basically half of the truss weight onto the walls, and that's from in addition with load combinations with snow, live, and dead loads. So that's how the load transferred onto that. And JL, do you want to answer his question about the reinforcing on the top side of our footings?
Yes, for the reinforcing on the top side of the strip footings, much of that was to meet the nominal area of steel required, as well as for just to get the required available moment strength in the footing for the design.
Just feedback, I encourage you to look at foundation design examples because the moment demand is at the bottom, it's going to then generate tension, demanding tension steel. So you don't have to answer, but I want you to go back and look at examples to see how you need to do the design to validate the outcome from this software.
Okay.
I'll ask a question. I'm not a structures person, so this is going to go in a different direction. But on your floor system rating, the analysis categories you had, were some of those subjective in nature? And if so, can you elaborate a little bit on any kind of engineering judgment you used to rate those?
Yeah, some of them were definitely subjective in nature. Cost was not, and sustainability was somewhat subjective. I read many research papers about that. And then for the structural performance, that wasn't as subjective. Both of those were had a decent amount of factor of safety on those. But then for constructability, that was really a subjective category because that was from contractors' experience, hearing about that and how simple the precast plank is to install, and also taking into account the time that's needed to install all of the joists and the deck on top of that, and then also the reinforcement for the slab and then the slab itself. It takes a lot of time there, so it takes a lot of effort from the contractor. And then the final category was compatibility with other trades, and that's mostly to do with the space underneath the floor system. We selected 24-inch joists and then a 4 3/4-inch slab on top of that, so that's taking up about 29 inches of floor space, and there's only 10 foot between the top of the first floor and the top of the basement floor, so we're really taking out quite a bit of room of headspace there, and also room for the mechanical trades. Whereas, so with the precast plank, there's a lot more room underneath the plank for mechanical trades to anchor into the plank. So it allows more flexibility and freedom of design for the mechanical contractor to install the ducts and plumbing and whatnot.
Okay, thank you.
And with that, we'll thank team 3. Thank you for the presentation.